All right, everyone, last class. So here we go. I forgot my watch, but that's okay. I'm just going to keep going till I'm done. Actually, I'm pretty sure we'll end early. And we're going to finish our discussion on how to write term symbols and this coupling of angular momentum. And let's see, also to answer your final exam questions. The last two questions I'm covering today how to do those. Okay. Now, I had to write some things on the board. I know it's daunting, but remember, I keep saying you chose to go to grad school, right? So let's review what we did last time. We did an example of, why did I do this? Of calculating term symbols on a, let's see, what would this be, boron or something? Something with just a 1p electron. Remember, term symbols represent the total angular momentum, which not only tells you the energy, is also a representation of the electronic structure, a unique representation. So that's fantastic, right? You know what it is and how much energy it has. Problem, when you make these little, is the electron in a PZ or a PX or a PY? You know how to do this. The problem is that these are not the energy eigenstates for all the reasons we talked about last time. So the term symbols that are so important to us, you can't look at any of these and know what they are. What you have to do is create linear combinations of them. Now we did a miniature example by coupling the spins of two electrons to show that they make singlets and triplets, and we showed why that is, because you have to diagonalize the S matrix, the spin matrix, and out comes singlet and triplets. Okay, so that was an example of adding angular momentum. Now, when it comes to this one, what we did last time was we figured out that no matter what, the term symbol has to be p. There's only one electron. It's only in the p state, so therefore the term symbol has to have, let me remind you that the term symbols look like 2s plus 1 L. Okay, there's only one electron, so S is a half, so that makes it a doublet. And again, all of those three states are all p states, and you can't do something like have. Remember, I told you a little bit last time that you can have something like this. We're going to cover this one today. If you have two electrons, then this would have an m sub L of plus 2, which means it cannot be a p state. That's impossible to be a p state and have an m sub L of 2. So this would be a d state. Now, when you only have one electron, like in this example, there's nothing to couple to in terms of L, so you're in a p state. So this wasn't hard to figure out the term symbol. Now, I don't know how much, I don't quite remember if I emphasized this, but the J is figured out by a simple vector this or that. What it is, it's L plus S to the absolute value of L minus S. What you're doing is representing, let me, L plus S minus 1, to the absolute value of L minus S. What you're doing is, that's just standard vector addition. And we're looking at the length of the vector. So the vector cannot, you can't have a negative. You can't have a negative. So L minus S absolute value. Okay, now in this case, learn by doing, right? So again, 2p wasn't hard to figure out. The J then is, okay, so S is a half, and S is a half, L is 1, so this is 3 halves. Now remember that we can also figure out, that's the J, and there's m sub J values. Okay, and that would be, now just like a P with an L of 1 has m sub L of 1, 0, minus 1, the J's are going to go from 3 halves minus 1, minus 1, minus a half, minus 1, minus 3 halves. Okay, so 1, 2, 3, 4. So there's 4 of these. And now, okay, so L minus S, 1 minus a half, that's 2p 1 half. And the m sub j's would be 1 half and minus 1/2. Okay, 1, 2, 3, 4, 5, 6. There's 6 states, and when you look up here, I have 6 states, so all of this makes sense. Okay, so that's all fine and good, but what I was going to tell you about today was, like for what I don't quite recall what I talked about last time. When it comes, what can be confusing, I got a little confused on this last lecture, is that this is how you do J's. Again, you're trying to show the absolute, the length of the vector. So that's why you do this L plus S to L absolute value of L minus S. But when it comes to the magnetic quantum number, then that behaves more like we're used to, where you go from L to minus L in increments of 1. So anyway, I hope that part's clear. All right, so we got to this last time, and I mentioned these Clebsch Gordan tables. The Clebsch Gordan tables tell you how to put these suckers together to make the actual wave functions, right? Now, it's great I got the term symbol, I got the right number of states. When it comes to which energy is lower, you actually have to look that up. That gets a little bit more complicated. It's got this thing called Hund's rules, which, like in the case of a half-filled shell, like this less than half-filled shell, the lower angular momentum is the lower energy. And if the shell is more than half filled, then vice versa. Look, I consider that stuff kind of stupid, and they're not absolute. You want to know what the real energies are? You use software like Gaussian or QChem or games. Even for electronic structure of atoms, you actually are going to want to do that. There are empirical rules, but I don't. Again, they were just like experimental observations that have lots of exceptions, so I don't care too much about those. Anyway, okay, now back to Clebsch Gordan coefficients and tables. I've drawn out the table here, which is painful, and so what I'll try to do, and hopefully I'm doing it right now, is I'm going to use the Premiere green screen to show the real table, and I will email that information to you as well. This table tells us how to construct the wave functions. All right, so let's see here. What do I want to do? I'm just thinking about how I'm going to edit this once I'm done filming. I guess I'll make the little thing go away, and I have to look back at my table because this is in front of me. All right, so I have 6 wave functions. Sorry, you know what? The first thing that you got to do is you got to identify the right table. The handout is rather complicated. There's a bunch of tables on there. All right, now what we got to do is, this case is simple in that we are trying to couple an L of 1, and the only thing to couple with is the S, which is a half. So you're looking for the 1 by half table. Now, this I know I may have made that easy. Trust me, it gets real easy to get confusing. Now, the way I know that this is the right table is, I mean, once I think of like, okay, what am I adding the angular momentum of? I then double check that I have the right number of states. So I know that I have 6 states. When I'm making linear combinations, you still have to have 6 states. And I see that this table has, these are what I'm looking for, these numbers here. Those are the 6 states. Okay, now how to read this. These numbers on top are the result of the addition of angular momentum. That's what you're looking for. The numbers on the left, so that's on top. The numbers on the left are these things, your bases. That's what you know. Remember, all of this is about, this is easy, you know how to do this, but those aren't the states of energy, and that means that they're not real. Okay, the top deals are the results of proper angular momentum addition, and those are the real states, the Hamiltonian states. All right, so now what? Okay, so let me do some examples here. And look at my notes, I don't screw this up. All right. So, now I'm not going to do all 6, I'm just going to do a few examples. And of course, you realize you're doing that on your final. Let's see, I will do 2p 3 halves, and I'll do m sub j 3 halves. Obviously I have to specify the mj. Okay, so 3 halves, right? Okay, when you look at the table, 3 halves, 3 halves. All right, so I can see what I'm looking for. It is composed of the +1 plus half. +1 plus half, see, it's right there. You see, it's actually kind of easy. It's actually kind of fun. Okay, so that means that this wave function is 1, the coefficient's 1. And you know what? I'm actually, to make it easy, I'm going to write out the configuration this way. It's this one. Now, I can figure out that wave function. Again, Google it. It's a 2p1, right? So I can look up the radial 2p wave function and the spherical harmonic for L1, M1, which is like 1 over the square root of 2 pi cosine. You see, I got the wave function. Okay, let's do a harder one. Okay, let's do 2p 1 half, 1 half. Obviously, there's 6 of them. Okay. Now I'll go back here. Okay, here it is, half, half. Okay. It is composed of the +1 minus half, right there. +1 minus 0, 1 half. This one, right there. Okay. Right? So, look, this is actually really easy. Take the square root of the numbers in the interior, and you read downward, by the way. Okay, so anyway, this will make it clear. Okay, so what do I got? I got 2/3 square root of +1 minus half, +1 minus half is, that is this one, minus square root of 1/3 of 0 half. Yeah. There we go. So, whatever the radial wave function for 2p. Oh, it's like, that's like e to the minus r over a naught. And the wave function for the spherical harmonic for L2, M0, I think that's just sine theta, some constants. You see how easy this is? Right, this is not hard at all. Now, one thing to note, the reason I want to cover this is that so many of you are inorganic chemists, and often when you're talking about transition metals with their ligands, the metal is still described using atomic term symbols, using these types of configurations. So that's why this is kind of important. Okay, so next one. Let us go to what's on the exam, which, and I also want to point out that, let's do what's on the exam. 1s2, 2s2, 2p2. I meant to mention this earlier. When it comes to term symbols and naming molecules, electronic states, naming atoms or molecules, electronic states, there's usually the lower orbitals are filled, unless you're in some excited state, some crazy excited state. The lower orbitals are filled. Now, even if I have a filled like P or D, when an orbital is filled, there's no angular momentum. There's no contribution. That means that they're dead in terms of contributing to a term symbol. If you had to generate the term symbol of something with a noble gas, right? Helium, neon, krypton, all that. Those would just be S states. They have no angular momentum. Singlet S, 1s, 1s0. So those are easy. When it comes to something that's a bit more difficult, like the situations we're dealing with, the 1s2 and the 2s2, you don't have to consider them. They don't contribute anything at all. Okay, so I just wanted to point that out. Okay, so we're doing 2p2, which is like carbon. All right, 2p2. Now, what I want to point out to you is that the number of states goes as this, TE, right? Yeah, I hate it when I see this damn thing. Okay, when you see a parenthesis with one thing over another thing, here's what it really is. I see this all the time. It's a shorthand for factorial something, something. Okay, T is the number of states, factorial, and what's on bottom is T minus E factorial, E factorial. E is the number of electrons. Okay, so when it comes to a P state, there are 3 of them, but then you have spin up and spin down, so that means that there's 6. Okay, so 6 factorial. Okay, there's 2 electrons, so that's 4 factorial divided by 2 factorial, which is 15. Get a calculator. on your exam, you have to do nitrogen, which has a T of 6 and an E of 3, and you're going to get 20 states. So, and I'm saying that because what you got to do is generate the same table. You're going to hate me for this. Okay, this is carbon. All right, on nitrogen you have to do the same thing, which is 20. It's not that bad. All right, look what I did. Plus, skip, plus. Oh, skip, plus. Then I did the same thing, minus. Okay. Then I did the obvious ones, double. And then it got a little bit harder. Plus, up, down, and then I flipped all those. Anyway, so it's not too hard. The main thing is to know how many you should find. Once you find that number, you should be set. Okay, now, term symbols. What are the term symbols for carbon? All right, first you need to know that you've got 15, in this case 15, you've got 15 term symbols to make. Now remember, if you have something like 3p halves, that's really, there's actually several states there. Anyway, okay, how do you begin? All right, now the first thing, I'm going to show you an algorithm, but you've got to have some sense about it. All right, now I mentioned several times. I'm looking at this thing, and I see an L. Oh, I wrote this wrong. This is 2. Oops. That's minus 2. Okay. I see an M sub L. So you see I've added up the M sub L's and the M sub S's. So these top blocks, by the way, they're triplets. If you have an M sub S of 1, you have to have an S of 1. You have to. You can't have a singlet. There's no M sub L for singlets. They don't exist. M sub L for a singlet of S of 1 of S is 0. M sub S is also 0. So I know that these on top are triplets. Cool. All right, so I got that. So I'm going to have triplets and singlets. I have 2 electrons. How could I not have triplets and singlets? All right, now I'm looking at this guy. I can see that I got a D state. M sub L is 2. Now, as much as it's composed of a P state, it's like, but I'm adding the angular momentum of 2 P's, right? And that's L1 plus L1, so that's 2. That's a D. So I'm looking at this and I'm seeing I got a D state. So now I got D states. I'm working with P orbitals, so I bet I got a P state. And I'm looking at that guy right here, 0, 0, and I bet you that's an S state. So again, what I'm describing, you don't have to do it this way. I'm just trying to build a feel for what I should get. Okay, next thing. What is funkier about this one is that using the Clebsch Gordan table, as we did last time, you can't just jump here immediately, because before I was just adding L and S, but here I need to add S's and L's, and then I use the table. All right, you see what I'm talking about? When it came to 1p, when I have 1p electron, there's only 2 things to add. There's the L and the S. Because I only have an electron, and there's an L and S momentum. Those are the 2 things that are added. Now I've got 2 L's and 2 S's, right? Because I have 2 electrons. The L's have to be added, the S's have to be added. I just gave you the answer on number 5. Anyway, and then when you have that information, then you can use the table. All right, now, I described a mess of stuff, but there's an algorithm to figure it out. So you don't have to think about all the things I just said. You just have to follow the algorithm. But before I use the algorithm, I just want to show you one more thing. Okay. Now the S's are going to add like vectors. So that's going to be S1 plus S2 dot 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 S1 minus S2. Absolute value, right? So remember, I'm adding these in the vector sense. We're not doing any M sub S's, right? Okay, so this would be 1, 0. So 1, 0 are my S's, singlets and triplets. But again, it's 2 electrons. Of course I have singlets and triplets. We talked about that last time. Okay, L. L is going to be L1 plus L2, dot, 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 L1 minus L2, absolute value. Okay, so 1 plus 1 is 2. Now remember, you go in steps. 1, 2 minus 1 is 1, 2 minus 1 is 0. and that's also L1 minus L2. 1 minus 1 is 0. And remember, you can't have negatives, because we're talking about the length of a vector. Okay, so again, I'm just trying to walk you through this. I haven't shown you the algorithm yet. I knew that because I have 2 electrons, I don't know their S's or L's, because I have to add them together. I know intuitively that I have singlets or triplets, and I can also do this. I have singlets and triplets. I know intuitively that I've got to have D states, just because I'm looking at that right there, I'm like, that's a D. I can do this, and I can see I've got D, P, and S. I got P's because I have P orbitals, and then I'm looking at that thing, and I've got to have an S. So you see, it's all working together. I got multiple ways to approach this. But let's do the algorithm, right? Because that's probably what you want. Okay, let me take a break and wipe out the board. All right, I'm back. Okay, here's how this goes. I'm going to make a table of M sub L and M sub S, but I'm going to put them on different axes. So let me show you what that looks like. I got this off Wikipedia, by the way. I never really knew how to do this until I read this Wikipedia article. They did a great job, and I'm going to send you that link. Okay, so let's do the M sub L's. And the M sub L's vary from 2 to minus 2. 2, 1, 0, minus 1, 2. Okay, the M sub S's vary from 1 to minus 1. 1, 0, minus 1. Okay, now what I'm going to do is I am going to count the number. So you see now I've got a matrix. I got a matrix. And what I'm going to do is add up the populations of, take 0, 0. 1, 2, 3. I got 3 0 zeros. 1 0. 2. 1, 2. Got 2. 2 0, just 1. These have to be symmetric, by the way. Okay, I've got a 1 1. Got a 1 minus 1. I got a 1 0. I better look this up. 1 0. 1 0. Looks like I got just one of those. I've got 2 of those. No, 0, 0, 1. What the hell is wrong with me? 0, 1. Wait a minute. I screwed this thing up. Look at this. Minus. Okay. That's why I kept getting, I got a 0, 1. I've only got 1, 0, 1. Okay. And I've got only one example of 0, minus 1. Why the hell did I write a 2 there? Okay, what about 1 minus 1? Only one example. Okay. Anyway, sorry. Forgot the little minus signs. Anyway, so is that table right? Anyway, I'll try to overlay, I'll green screen that table as much as possible, but don't look at what I did. All right. Okay, so here's the algorithm. So you make the table, you have 20 examples for nitrogen, and now what you want to do is just decompose it. Now again, I know that the thing that can be confusing is getting a little bit lost about adding these up as vectors versus the, S versus M sub S, L versus M sub L. Okay, I know that's a little confusing, and I think I've got it straight. So when I'm looking at this, I need to start pulling things out of it. Now what I see is the maximum length in M sub L is 5, right? MS sub 0, M sub L of 1, 2, 3, 5 members. Only a D state can have 5 M sub L states, right? So what I'm seeing is a D state 0, M sub L, 2, 1, 0, minus 1, 2. And if I take out 1, okay, so I'm going to rip one unit of membership out of the central column here. Okay, so I'm looking at this, so I'm subtracting, from this I'm subtracting that, and this is clearly a D state. Now the M sub s is 0, so that means it has to be a singlet. Right? If it was a triplet, I should have an M sub s of 1 and minus 1 including 0, but I don't. That is clearly a singlet D. Okay, now what I'm going to do is then reduce the interior by 1. I'm not writing here, I'm just leaving it blank. Okay. Now what I see, I got to keep going until the table's empty. Now what I see is a 3 by 3. And M sub s now varies. It's a little bit more interesting than just 0. Okay. And it looks like I can pull one member out of each one of these. Okay, now, there's two things to note about it. I'm pretty sure it's a p state because M sub l goes from 1, it goes 1, 0, minus 1. That's a p state, px, py, pz. Okay, so it's a p. M sub s goes from 1, 0, minus 1. That makes it a triplet. Right now, double check. How many states are there? There's clearly 9. Does that make sense? The number of triplet states is 3, and the number of p states, px, py, pz is 3. 3 times 3 is 9. There's 9 states. There you go. All right, so now let's wipe that out. Again, I'm just gonna, I leave the tables empty. It confuses me to see a bunch of zeros. Okay, there's only one state left, which is M sub L of 0 and M sub S of 0. And one member that's clearly a singlet S. Ta-da! All right, now we're done. That's the algorithm, right? It's not hard. And when you do it, it won't be terribly difficult. Okay, let's do the J states, the lower B. Okay, now J is it's L plus S, and let's see here. S is 0, L is 2, so J is 2. Now recall that means that there's actually 5. So actually, here's another thing. Let's make sure we have 15 states, right? Okay, we figured out it was singlet D. The only J possible is J of 2, but remember that means that there's actually 5. 5 J states, right, because of M sub J. M sub J, if J is 2, M sub J is 2, 1, 0, minus 1, minus 2. So there's 5. Okay, triplet P. S is 1, P is 1, so that's also, I'm going to cheat because actually it's kind of, oh, no, wait a minute. Wait. Sorry. Gotta be more careful. What are the J states, right? L plus S to L minus S, absolute value. L plus S, 2 plus 0, 2S plus 1 is 1, that means S is 0. So there's only one J state. Kind of messed that up. Okay, well, I mean, I got it right, but I forgot to check whether there's more than one. Okay. L plus S is 1 plus 1, 2S plus 1 is 3. So S is 1, L is 1. So I can have a J of 2. Now remember that the J states are like vectors. So I can have L plus S minus 1 to the absolute value of L minus S. I've said that many times, right? That means that I've got a 2, 1, and 0. L minus S is 1 minus 1 is 0. Okay, so 2, 1, 0. So I've got, now let's see here, how many states? A J of 2 has 5 states, a J of 1 has 3, and a J of 0 has 0. Right, M sub J, 2, 1, 0, minus 1, minus 2, 1, 0, minus 1, and just 1. So 5, 6, 7, 8, 9. There's 9 of these, and of course 1 S has to be 0, and there's only 1 of these. Okay, 5, 9, 14, 15 states. We have 15 states. 15 configurations and 15 term symbols. Well, kind of. I mean, well, anyway. So you usually just express it this way. All right. Now, last bit, we're almost done, I told you to end a little early, is now I want to start writing the wave functions out like I did last time. And guess what? This is going to be a little bit of a pain. This is a little bit harder than you realize. And here's what's going to happen. We're going to look at the Clebsch Gordan table, and we're going to look at. We need to look at three tables technically. Right? We need to look at three tables. I've got an 1 by. I think this is 1 by 1. I'm praying I'm not screwing that up. 1 by 1. S is 1. L is 1. And then I've got a 1 by 0 and a 2 by 0. Okay. Now it turns out that let's focus on this one first. And there's a good reason for that, and I'll explain in a minute. So we're going to come up with the wave functions. We're going to look at the Clebsch Gordan table for the P states. And that's 1 by 1. We're looking at the 1 by 1 table. And hopefully that's appearing right now if I've done my editing correctly. Okay, what I'm going to do is I'm going to take a break, and the table's too big for me to write on the board. So I'm going to just write some snippets, and we're going to go from there. All right, so I'll be right back. All right, everyone, I'm back. So I am only going to write part of the Clebsch Gordan table. I'm not going to solve for every wave function clearly. Again, there's 15. I'll do a couple to show you that you're going to run into a slight problem here. And I'm just going to give you the answer, and I'm giving you the answer number 5, but whatever. All right. Okay, so now I've got to write the wave function. Now I know that I've got a 2p, let's say I know I've got a 2p2, is that right? No, it's a triplet, what am I doing? I wiped it out. Triplet P2, wrong, triplet P2. Okay, and remember that there is a 2, 1, 0, minus 1, minus 2. Those are the M sub j. M sub j's. So I'm going to pick one. So I'll do a triplet P22. So highest angular momentum possible. Okay, now look at the table. Okay, now I'm looking at the 1. L is 1. S is 1. 2s plus 1 is 3. That's triplet. L is 1 is P. All right, so I'm looking at the right table. And the Clebsch Gordan table has, guess what, 9 entries. 9 entries. 1 by 1 has 9 entries. And there's 9 triplet P states. So I know I have the right one. Okay. Now, so the wave function for the 2-2 term is composed of a single configuration, which is plus 1, 1. Let's go over here. 1, 1. This wave function. Ta-da! Easy. Okay, let's pick a harder one. Let us do 2p, triplet P. I just didn't write it out right. That's a triplet P. Okay, let's do the j of 2 and sub j of 1. Right, that'll be a little bit more difficult. Okay, and I happen to have wrote that entry here. It's not where it appears on the table, but anyway. Okay. Now I've got, let's see, remember you take the square root of these deals. They literally don't write square root just to make it more readable. It actually says that. Okay, 0 plus 1. Okay, you see this isn't hard. 0 plus 1. And again, instead of writing e to the minus r over a naught, I'm literally just going to do this. Up. Okay, plus square root of half of 1, 0. All right. 1, 0. Oh no, there's 2 1 zeros. That's a bit of a problem. Why have I got 2 1 zeros? it turns out that there's another place that this appears, which is going to be 2D. What is wrong with me? It's singlet D. Let me check my own notes. Jesus, for some reason I want to make everything, I know I want to make everything a doublet. I want to make everything a doublet because of, the previous example, everything was doublet. Anyway, okay. So singlet D, D of 2, but there's 5 of those. Let's do 2, 2, 1. Right, we did 2, 2. 2, 2, right, this is D, singlet D. I can see that's a singlet state. And you know, here's the thing. Let me back up a bit. So I'm just trying to figure out why I have this problem. Why I need, according to Clebsch Gordan, a 1, 0 state, but I see that I have 2 1, 0 states. Up, down, and then down, up, right? Up, down, up. Let's see here. Okay, hold on. These are triplets. Okay, they're definitely triplets, right? Because m sub s is 1 or minus 1. It's not 0. So these are triplets. I know that I have 9 triplets, right? But look, there's only 6 states. Only 6 states. Now these 3, let me mark that. These are triplets. They have to be. Now, these are singlets. They have to be. The electrons are paired. Okay. Okay, now let me think about this. 1D2 has 5 states. 5 states. And then I've got a 1s0. 6. 6 singlets. I have 6 singlet states, right? 5 1Ds and 1 1s. 6. 1, 2, 3. I've only got 3 identifiable singlets, so I'm missing 3. Okay. 3p, whatever, has 9. I've got 1, 2, 3, 4, 5. I've got 6 obvious triplets. I'm missing 3 for each, for a total of 6, and I have 6 remaining states. Okay, so here's the thing. And guess what? Here's in that weird bracket, that's where my 2 1 zeros are. So the weirdness is all kind of, I have some weirdness, and it's all showing up. It's all showing up right here. Okay. Now I've got to tell you something more about the D Clebsch Gordan. There isn't one. When one of the angular momentums is 0, there's nothing to do. The table is there is no table. There's nothing to couple to. Remember, Clebsch Gordans tell you how to add angular momentum, right? But if one of the angular momentum is 0, meaning it's an S, then there's nothing to add. There's nothing to do. Okay, now the D is a singlet state. So that means that I'm not making linear, I don't think I'm making linear combinations of anything. Okay, so there's my D, singlet D 2, 2. Here's my singlet D 2 minus 2. J of 2, M sub J of minus 2. Okay, I see those 2. Now I need 3 others. I need a 1, 0. I need a 1, 0, and then I need a minus 1. Yeah, a plus 1, a minus 1, and a 0, 0. Right? Yeah, because I got 2, 2, 2 minus 2, and I need, yeah, anyway. So here's the thing. This needs to be a 1, 0. 1, 0 configuration. Okay, so again, 0, this has to be 0 because this D is a singlet state, and the M sub L has to be 1. Now, the Clebsch Gordan told me that this triplet P has a 1, 0. Okay, so here's the nature of the problem. Again, 3 identifiable triplets, 6 identifiable triplets, I'm missing 3. 3 identifiable singlets, I'm missing 3, and I have 6 remaining states. The nature of the problem here, I first identified that the Clebsch Gordan says I need a 1, 0 state, but I have 2 of them. I don't know which one it is. Now, the Clebsch Gordan table, there isn't one for the singlet D, but I know that it's 2, 0, 1, 0, 0, 0, minus 1, 0, minus 2, 0. Again, 2, 0 is obvious, that's a D state, it's obvious, that's a D state, so 1, 0. Okay. Now, what's kind of cool about this is I see that one of these 1 zeros belongs to the triplet P, and the other one belongs to the singlet D. Triplet P, singlet D, but which one is it? Let me look at these again. Let's look at the 1, 0. Let me look at both of them. Up, down, and the other guy is down, up. Now my job is to look at this and figure out which one is singlet, which one's triplet. The triplet will belong to P, and I'll put that configuration. Maybe it's this one. I'll drop that there, and that makes that the singlet, and I put this here. But I'm looking at this, up, down, up. Why the hell are those different? How can I say one is singlet, one's triplet? It doesn't make sense, does it? Here's the screw up. When we made that little matrix table and figured out we had a DP and S state, we were adding the L's, but we never added the S's. You have to add, you have 2 electrons, you have to add their L's to a total L, then you have to add their S's to a total S, and then you use this freaking table. But we've jumped the gun, haven't we? Now we added the L's together, but we didn't add the S's. Okay, remember this? Remember the situation we were in before? When we talked about a 1S and a 2S, and we had up, down? And what do you do? If you add down, up, you get a triplet. And if you up, down, and you subtract down, up, alpha, beta minus beta, alpha, you get a singlet. Remember that from yesterday? Again, up, down, plus down, up plus down, up is triplet. Up, down, minus down, up is singlet. Up, down, plus down, up. That's our triplet. Okay. Of course, the half, right, with square root. So I'm going to do 2 plus this triplet. There we go. See, you have to add the S's first. Okay, and then this guy, of course, is this annoys me. Okay. That doesn't look good. There we go. Minus. Down. There we go. You had to make linear combinations in the S manifold first to make sure you could identify your singlets and triplets. And once you had done that, then you can see that your 1 zeros, you have 2 of them, which combine to make triplets, which goes to your triplet P, and then the leftover is a singlet, which goes to your singlet D. It all makes sense. Now you also, now assuming that this 0, 0 is the 1s0, it's unique, right? And this is clearly unique. You got 2 0 zeros, make linear combinations of them. One of them belongs to a triplet P, and the other is the D2 0 state. And the same with the -1. Let's see, you've got 2 minus 1 zeros, right? And so you do the same trick. So that's how you build your D manifold. Again, you have to do that without a Clebsch Gordan table. And the P, you have a Clebsch Gordan table, but we've seen plenty of times how to do that. Okay, last but not least, now unfortunately we're going to go into the land of horrific confusion. I actually don't have an answer for what I'm going to tell you next, which is how to energetically order these. Here, I'm just writing down the terms. Again, 5 states, 9 states, 1 state, 15 states. Okay. we have done what's called L plus S coupling. So the way that works, the way it works is what we just did. I want to give you a drawing to kind of remind you. When we made that crazy table, we basically took two different L's, L1, L2, and we coupled that to big L. And then we took S1 and S2. We did that second to make big S, which was then coupled to our final J. Okay, so that's called L plus S coupling. Figure out your L's, figure out your S's. Okay, make term symbols. I'm guessing you're familiar with these. You can energetically order these. Now, that's where things get crazy. Typically, triplets are the lowest energy. Now, that's because of we haven't spent any time, hardly any time, talking about the Hamiltonian of an atom. But it turns out that the Hamiltonian of an atom has the kinetic energy and the Coulomb part, but this thing called for two electrons, you have an exchange integral, which has to do with the symmetry, the anti-symmetry of a wave function. Hopefully you remember this from your undergrad, but electron wave functions in atoms, when you have more than one electron, they have to be symmetric with respect to, anti-symmetric with respect to interchange. Basically, if you change the labels on electrons 1 and electrons 2, you have to have the same wave function times minus 1. Now, if you haven't heard of this, that just blew your head off, I know. What that does, that thing that just blew your head off, it prevents this from happening, up. You can't have up in the same orbital. Like, this is 1s. You can't have 1s alpha. You can't. When you write wave functions out in an anti-symmetric way, anti-symmetric to interchange, that never happens. Okay, so what? Because you write the wave function this way, you have two Coulomb integrals. One that's normal, just electron 1 interacting with electron 2, and another one which is called the exchange. The exchange generally lowers the energy of triplet states and correspondingly does nothing or raises singlet states. Triplets tend to be lower energy than singlets. So that's why I'm picking this one to be the lowest energy state. Now, then you get into those crazy rules. I mentioned them a minute ago, that like if the orbital is half filled, less than half filled, then the lowest J state is, the smallest J state is the lowest energy, and if the orbital is more than half filled, blah, blah, blah. I don't even remember those, and I think that's very empirical, and I know there's exceptions, and I don't care. Right? I would use a computer to do that at this point. So anyway, so there's rules for energetically ordering these, and personally I don't care. Now there's another part of the Hamiltonian. For light elements, we haven't considered it. It's the spin-orbit coupling, right? I talked about spin-orbit coupling a while ago. I have not, if you do any spin-orbit coupling with this, again, you can get splittings between like the 2, 1, 0, minus 1, 2, you know, you can do tricks, you do more tricks with these. Okay, and there's rules for that. Well, the Hamiltonian is LS, which is J squared minus L squared minus S squared. So that means that the lowest J, that means that the lowest J is going to be, oh, that's where that comes from. The lowest J is the lowest energy state. It's the spin-orbit coupling that does that. Okay, now here's where things get nutty. Spin-orbit coupling, the expectation value is proportional to z to the 4. What happens is, if the atom gets heavy enough, spin-orbit coupling is more important than the Coulomb and exchange part. So that means you have to make things, before you add them together, they need to be okay with the spin-orbit coupling first. Now, I did not do that here. I've made these are all states of J, but they were created last. I said L and S are well known, and then I added them to J. If spin-orbit coupling, and then I can do like spin-orbit coupling by perturbation theory, and I would know that the J of 0 state is the lowest. So the triplet is the lowest because of exchange. Spin-orbit makes the the J of 0 the lowest because of spin-orbit coupling. It all makes sense. However, if spin-orbit coupling is dominant, Again, I consider spin-orbit coupling last when it comes to ordering these term symbols. If spin-orbit coupling is very strong, you don't consider it last, you consider it first. To make spin-orbit coupling work, you have to figure out what the J's are early on, and then you couple them. All right, now what, and that's like, all right, but what does that mean, right? Okay, let me show you. We're going to do an example. We're going to do, so this is called JJ coupling. So what you just saw was LS coupling. Let me give you a diagram. Let me draw a picture of it first. What you do is you're going to couple L and S. So what we're going to do is we're going to use the Clebsch Gordan table on single electrons, considering their L and S. We're going to figure out J of the electron 1, and then we're going to figure out J of electron 2. And I'll draw that here. So here's J1. And then we've got ourselves L1, L2, S2, and that's J2. And then big J is composed of J1 plus J2. So remember before, I added the L's, I added the S's, and then I figured out J. Here I'm adding the L's and S's, to make J's that add to J. Example, right? We'll do an example. Examples will make all this better. Okay, I'm going to pick an easier system because I think we're almost out of time. Okay, let us do 1s, single electron, 2s, no electrons, I'll put it in the 2p. Okay, so a little bit easier, but there's some complexity because I've got a p state. If I did 1s, 2s, there's really nothing to do. Okay, now we know that there will be 6 combinations. There will be 2 combinations. What I'm doing here, I am counting up the number of states because if I lose track of the number of states, I'm definitely doing it wrong. I always keep track that I have the right number of states or I'm blowing it. Okay, 6 combinations because we just did that, right? 2p1. Up, 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 down, 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 6. Up, down, 2. So there are 12, 12 states. Up, 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 down, 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 up. Up, 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 down, 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 down. 12. There we go. Makes sense. Okay. Okay, so, let's see here. What am I doing? Let me remind you in LS coupling so we don't just completely lose our minds. In this case, so you can, okay, so LS coupling, this is what we were doing. This is when spin-orbit coupling is small. We're talking about first, second, third row of the periodic table. Your S is S1 plus S2. S1 minus S2. Okay, here. It's 2 electrons, so it's going to be 1 and 0. We've got, when you have 2 electrons, it's singular and triple. Okay, L is L1 plus L2. Okay, that is 1 plus 0, 1 minus 0, so that's 1. Is that right? Okay, so that's a p state. So I've got singlet, triplet, and I've got p states. Okay, so therefore, what I've got is a triplet p, and let's see, 1 plus 2 is 2, that means I got 3p1, 3p0, and then I've got a singlet p, and 1 plus 0 is 1, 1 minus 0 is 1, okay. Let's see, 5, 8, 9, have I done this wrong? 5, 8, 9, 10, 11, 12. Right, there's actually 3 of these. Is that right? Yeah, it's a p state. It's a p state. Of course there's 3. What's wrong? Yeah, there's 3 of these. That's J. M sub J is 1, 0, minus 1. That's 3. Okay. 2, 1, 0, minus 1, minus 2, 5, minus 1, 0, 1, 0, minus 1, 8, 0, 9, 1, 10, 0, 11, minus 1, 12. Okay, there's 12 states. Okay, again, so now you see how easy this is. All right, but now let's do JJ. Let's do JJ couple. Okay, so what we're going to do is let's look at this guy. Okay, let's do this one first. Okay. Now, in this case, what we're going to do is J1, which is going to be L1 plus S1. If we're going to call that the first electron, actually I should have called that the first electron, but whatever. Okay, to L1 minus S1. It's arbitrary, by the way, which one you do because of the absolute value. You could say S1 minus L1, it doesn't matter. Okay, what do you get? Okay, 1 plus a half. It's a p state. L is 1, S is a half, so that would be 3 halves. Okay, then 1 minus a half would be 1 half. Now notice that, all right, so I'm done. There's no S, there's no P, there's no singlet, there's no triplet. And that's one of the things that you lose when you are doing JJ coupling. The effective spin orbit coupling means that you can't say whether something is singular or triplet anymore. You completely lose that, and that sucks. But that's how it is, trust me. We think about phosphors that are spin forbidden. We think about spin forbidden. We're always talking about spin forbidden processes. Nothing is spin forbidden when you have JJ coupling going on, when an element's heavy. Because the way you add the electrons, you no longer have distinguishable S. Okay, now let's do J2. As usual, the vectors add this way. Okay, 0 plus a half, 0 minus a half. That's just 1 half. There's no minus a half, right? Okay. Now, so we're not done. These are like the basis states, right? This is just like when I first figured out my potential S's and my potential L's to get the term symbols. I've now done these guys. I don't have any nice term symbols for them, but now I need to do the J1 plus J2 addition to get total J. So total J is now J1 plus J2, J1 plus, just to remind you, J1 plus J2 minus 1, to J1 minus J2. And, okay, let's see what happens there. Okay, so this ends up being, sorry folks, I just lost my mind there for a second. So we're still doing the J states. Okay, now the way you do this is, we're going to take these and add it to these, right? Because these are the 2 electrons. Okay, again, I guess this is a little funky even from my perspective. Okay, we have 2 possibilities for the first electron and only 1 for the second. Okay, that means I actually have to do this twice. Let's say that J1 is 3 halves and J2 is 1 half. Okay, sorry, plus, right? Okay, so that's 2. The 3 halves minus a half is 1. So 2, 1. Okay, so the final J is 2 or 1. Now, I've got J1 plus J2, where I've got 1 half and 1 half. And therefore, that's 1 and 0. Therefore, the final J's are 2, 1. There's 2 1s and 0. Okay. Alrighty. So with that, Actually, I don't, I am not really very comfortable with J states, but here's the deal on how this works. Let me draw you a little bit of a configuration here. Let's look back at, okay, so we were just doing our 2S1, 2P1, 1S1. Okay, for this example, our LS coupling gave us triplet P's, and again, that will be the L1, 2, 1, 0. That's the lowest energy. We've got a 1P, and of course that can only be 1. There's 3 of those. And what was there? That 9 of these, is that right? I think that's right. Okay, so this is the LS. So this would be like on the first row, or second row. Okay, now what happens is that spin orbit coupling does things like this. It makes the lowest J state lower in energy. Then you got 3P1. Then you got 3P2. Okay, so this is spin orbit. Now again, it's weak, so I haven't split these up very much. Now the 1P, that's weird, isn't it? So the 1P1 is higher in energy, and again, that's actually because of the exchange interaction. I know we haven't spent much time on that. You really should probably look that up a little bit more on your own. Okay, for JJ coupling, we just covered that you can have a 0. Let's see, J of 0. The way you write this is you put a 0, and then you put what coupled to what. So the half-half. Electron 1/2, electron 2/2 would give you a J of 0. And that is actually coupled to the 3P0 state because both their J's are 0. Right? Remember, this is J of 0, that's J of 0. So these are related. Okay, then you can have a J of 1, which is, of course, the other half-half state, because half and half can add or subtract, and that will couple to this state, to 3P1. Okay. Now, and again, using rules that I don't really know, the J of 2 is going to be higher energy. And of course, that comes from 3 halves and 1/2 adding together. And that, of course, has to be related to the J of 2 state. And that also leaves us, the last state is the J of 1 state from the 3 halves, 1/2. When they subtract, and that has to be related to our residual 1P state. Okay. Now the way it works is, let's say you're looking down the periodic table at elements with a 1S1, 2P1, that would be an excited state of an atom. Now you do all kinds of crazy spectroscopy. And if it's light, you would see this kind of splitting. Not much splitting. When you go down the periodic table to an element with the same electronic structure, you would see energetic splittings that correspond to this configuration, which is different. Like the pattern is different, the spacings are wider. You would spectroscopically observe that. And that's because the spin orbit coupling is so large that you can't ignore it. You have to diagonalize your Hamiltonian with the spin orbit coupling, meaning get the J states first, and then you add them together like you add angular momentum together, and you get a completely different pattern. And again, in terms of ordering these in energy, I know some things about this, right? It's exchange interactions that favor triplets, And the J states, if the orbital is less than half fill, are the lowest J states or the lowest energy, blah, blah, blah. I don't remember. J states, I have no idea. I have no idea what the rules are. You can look them up. There's rules for which J state is the lowest energy. You look them up, or better yet, calculate it. Anyway, okay. That is all about angular momentum, and I think you see why I waited till the very end to do this, and I hope that I've covered enough. You can absolutely for certain do your final exam